Alrighty, so tonight we're going to be talking about introducing the new topic, equilibrium. And like thermochemistry, you can get rid of the other stuff. Like thermochemistry, it is a bit of a complicated topic, so you guys are going to want to focus and listen and try and get the details down. We are going to do an activity tomorrow in class, though, that I think will really help to solidify the concepts that we're talking about tonight. So, Sam, you're good. All right, Jason, you're good. Keep open it, slam it, it's fine. And you're going to hear your name now. All right, let's talk about reaction rates. I'm getting a little punchy. I've had some caffeine. So, all reactions occur at different rates. This is something that you guys, I think, all instinctively know. We haven't really talked about it, but you should know this as just observers of reality. For example, striking a match causes it to erupt into flame almost immediately. There's no real delay, it's almost immediate, whereas converting dead plants under the surface of the earth into coal takes millions and millions of years. So every reaction that you're looking at has a different timeline or a different rate that it occurs in. Reaction rates, we can define it as the measure of speed of any change occurring within an interval of time, where the interval of time can vary. So it's important that you know that there's no specific time length that we're talking about. It's just any interval of time. And they're measured in amount of reactant changing per unit time. So the rates of chemical reactions are related to properties of atoms, ions, and molecules through an idea called collision theory. And collision theory states that atoms, ions, and molecules can react to form products after colliding with each other, providing the colliding particles have enough kinetic energy. So the whole idea of reactants colliding together, we all know that all molecules and particles are vibrating at some frequency and moving with some kinetic energy. But if they collide with enough kinetic energy, they can actually go on to cause these reactions that we've been talking about all year long. Now, that enough energy that we're talking about is the activation energy that we just talked about in thermochemistry. And so that activation energy is the energy required to break the bonds, the energy required to make the reaction happen. And up at the peak, so the peak of our activation energy, where the reactants are going to go over and start forming products, we momentarily make something called an activated complex. So again, activation energy, we've talked about it, and we form something called the activated complex. So this is just kind of a quick review over the stuff that we learned in thermo. Now, the activated complex is an unstable arrangement of atoms that forms momentarily during a reaction if the particles have sufficient energy and they're oriented correctly. So not only do they have to have enough energy to overcome that activation barrier, but they also have to be oriented in the correct position in order for this activated complex to form. So it's definitely something that doesn't always happen. Activated complexes have an average lifetime of about 10 to the negative 13 seconds. Now, these activated complexes are often what we are solving for when we're calculating using Hess's law. And the reason being is that because they're short lifetime, we can't directly measure their Q, so we will do it indirectly. And so it's these activated complexes that we're often solving for. So connection to stuff you've already learned. Woohoo! So the activation complex ends its lifetime in the reformation of either the products or the reactants. Both of these outcomes are equally likely. So it's important to know that that activated complex, when it dies, if you will, it's either going to go back to being a reactant or go back to being a product. And so either one of those options is equally likely. So we then in chemistry start using stuff called equilibrium, and this is kind of what we're going to be looking at, is figuring out, okay, so if they're both equally likely, is there a way to figure out which way it's going to go? So let's look at some factors affecting reaction rate. And we're going to start talking about the likelihood of it going to products and reactants later, but right now we're just going to start talking about reaction rates and how they can be affected. So every chemical reaction proceeds at its own rate, naturally. Some fast, some slow. By varying the conditions at which the reactions are occurring, the rate of almost any reaction can be modified. As always, there are always exceptions, so that is something to keep in mind. But most of the time, you can change the rate of a reaction by varying some of its conditions. The following are the conditions that you can vary to affect the rate. One is the temperature. It's kind of obvious. Concentration is also one, and I put these fancy brackets next to it because we use brackets as a shorthand to indicate concentration, and you're going to have to use these when we start doing calculations, so I'm trying to get you used to the idea of brackets being related to concentration. Particle size also affects reaction rate, as does the use or non-use of a catalyst. So let's look at how these factors actually affect rate. So as you increase the temperature of a reaction, the reactant particles are moving faster and more chaotically. When this happens, an increase in the frequency with this comes an increase in the frequency of collisions and an increase in the number of particles with enough energy to overcome the activation barrier. So because they're moving faster, they're having more collisions, and because they're moving faster, more of them have the energy required to overcome that barrier. So an increase in temperature causes an increase in product formation. So if you increase temperature, you're going to be increasing the amount of product that's being formed. Let's look at an example of that. At room temperature, a bag of charcoal in contact with air is not just going to spontaneously burst into flame. However, if you put a starter flame and it touches one of the charcoal, atoms of carbon and oxygen will collide with each other with greater energy and greater frequency. Some of these collisions are going to be of high enough energy to produce CO2 and actually go through that combustion reaction. Heat released by the reaction then supplies enough energy to get more carbon and oxygen atoms over the energy barrier so that when the starter flame is removed, the reaction continues. So it's this idea of when you increase the temperature of the reaction, you start moving around frequently, more rapidly, you're going to have more frequent collisions. The energy is going to be higher because of the increased temperature, and so more of these collisions are going to be of high enough energy that you can go over the activation energy barrier. And then because it's producing its own energy from the reaction, that provides energy to more carbon and oxygen atoms to create more collisions that are going to overcome the barrier. Okay? Now if we look at concentration, the number of particles in a given volume, or the concentration, does affect the reaction rate. If the number of particles of reactant is increased, the concentration of the reactant increases, and therefore the frequency of collisions increases. And with an increase in frequency of collisions, there's a greater likelihood that more of those collisions will have enough energy to overcome the activation energy barrier, and therefore the rate of the reaction will increase. Now it's important that you keep in mind that this is not the same as increasing temperature. Increasing temperature actually adds energy. More of the collisions are occurring at higher energy because you added energy to those collisions. In concentration, it's not a matter of adding energy to the collisions, but more a matter of statistics, in that if you increase the number of collisions, statistically, more collisions will then have a high enough energy to overcome the barrier. So you're not actually increasing the energy of the collisions so much as you are increasing the likelihood or the statistical probability that there will be collisions with higher energy. So an example of this you actually did yourself in the micromole rocket lab. In that lab, you held a glowing splint in air and saw that a glowing splint will just glow in air with the oxygen around it. Then you stuck that inside a pipette bulb full of just straight oxygen gas. And so with a greater concentration of oxygen gas available, that glowing splint burst into flame. And so that reaction rate increased. Instead of just a few reactions going on to keep it glowing, it burnt and it burst into flame because you were in a greater concentration of oxygen. All right, now let's talk about particle size. The surface area of a reactant particle affects the reaction rate. Now, with a decrease in particle size, there is an increase in surface area for a given mass. So if I have one big ball of, say, calcium, I've got a little slab of calcium oxide, which is marble. Now, if I've got a big chunk of it and it weighs 10 grams, that big chunk, the surface area of that is going to be smaller than if I took that same 10 grams of marble, broke it up into little teeny tiny pieces, and then had each of those teeny tiny pieces had a surface area. And by breaking it into smaller pieces, I now have more surface area because all that stuff that was on the inside of the really large 10-gram block is now all exposed and able to have its own reaction instead of being inside. I hope that makes sense. I'll do some hand gestures. I'm doing them right now, but you can't see them. I'll do them in class tomorrow, and that'll make more sense. But a decrease in particle size increases the surface area. And increasing the surface area increases the amount of reactant available to react, and therefore increases the collision frequency and the reaction rate. So increasing surface area increases the reaction rate. Now, this actually can kind of be bad in terms of coal miners. The coal dust that they break coal into can, because it's so small and has such a small surface, or it's so small, they can inhale it, but it has a larger surface area, so more of it's able to react and cause all those horrible things like black lung and lung cancer and all of that nastiness. So, not all chemistry is good. All right, catalysts. So, increasing the temperature is not always the best way to actually increase reaction rate. Sometimes it's better to use a catalyst. Catalysts are used as a method of increasing the rate of a reaction, and it's beneficial because catalysts, the whole point of them is that they are not used up during the reaction. And this is a diagram that shows you two different methods of going through a reaction. The black one shows you just the regular products to reactants method of you've got this activation energy barrier and you're going to make products at a lower energy. The red line shows us the addition of a catalyst. I was going to put the word catalyst there, or no catalyst in catalyst. I totally forgot to, sorry. So what the catalyst does is it doesn't actually change the energy required to do the reaction. It doesn't change this reaction. It just provides an alternate route. And this alternate route has a smaller activation energy. And so by having an alternate route with a smaller activation energy, more collisions will be able to overcome, will have the energy required to overcome this barrier than this barrier. And so more collisions are gonna go over this slope and become products than going over this slope. You'll notice though that the delta H is still the same. So we're not actually changing the reaction, we're just providing a lower alternate energy path for the reactants to take in order to become products. Now, so far we've always inferred that chemical reactions go completely from reactant to product. In reality, this is not usually the case. Some reactions are what we call reversible, meaning that the following reactions are occurring simultaneously. Reactants are becoming products, and products are becoming reactants. These are reversible reactions. What this means is that if I had an example of sulfur dioxide plus oxygen making sulfur trioxide, this reaction would be going in the forward direction, whereas we also would simultaneously have the reverse reaction of sulfur trioxide becoming sulfur dioxide and oxygen. So you have the forward and reverse reactions going at the same time. We normally write these in chemistry utilizing the following special reversible arrow. Oh, look at it, it's so pretty. It looks like two half arrows, one pointing in the forward direction, one pointing in the reverse direction. And it's important that you draw these as half arrows, not full arrows, because I don't know, I'm picky about it. That's why. I could come up with some baloney excuse as to chemical community and whatnot, and you guys would never be able to refute me. But what I'm just gonna say is that I'm really, really picky, and I like the half arrow because it shows you that, I don't know, it's how I was taught, guys. I can't give you any explanation other than it's just how I was taught and it's how I like it. So that's what we do in the chemical community. So let's talk about this. When you have this reversible reaction, eventually the forward and reverse reactions start to occur at the same rate. So just as much product is becoming reactant as reactant is becoming product. They're occurring at the same rate. This is called chemical equilibrium. And what's happening here is you can see that in this side we start out with some concentration of oxygen and some concentration of sulfur dioxide. And those concentrations decrease over time until they level out. And as those concentrations are decreasing, it's because we're forming more product. So reactant concentration decreases as product concentration increases, and eventually it reaches this peak where it levels off and you're not changing concentration anymore. Alternately, we can start with some amount of sulfur trioxide and no amount of sulfur dioxide and oxygen, and as the reaction goes in the reverse direction, it eventually levels off and we build in sulfur dioxide and oxygen as we get rid of it. At chemical equilibrium, there is no net change in the amount of components in the system. So that's this whole idea of these level off at some point, and if you add these together, there's no change in the total amount of components in the system. Now, when we reach that is called a dynamic equilibrium, and that's at these points where the graph has leveled off, so in these two areas. Now, dynamic equilibrium, or unchanging amounts of SO2, O2, and SO3, does not mean the reaction has stopped. Rather, the equilibrium has reached a dynamic state. What a dynamic state means is that both the forward and reverse reactions are occurring at equal rates, or we've reached chemical equilibrium. So I've created this little graph, or this little picture, and we're going to talk about it in a second, and I really am very proud of it. I made it in paint. It's original Kelly Henry art. You should treasure it forever. Now, this little drawing is of an escalator, the up escalator and the down escalator. And you've got the first floor and the second floor of some department store. Now, you'll notice here that the up escalator and the down escalator both have the same number of people going up and the same number of people going down. You could consider this the same rate. The same number of people are going up as the same number of people are coming down. This could be equivalated to chemistry by saying that the rate of the forward and reverse reactions are equal. So at this point, we are at dynamic equilibrium or chemical equilibrium. We've reached an equilibrium where the forward rate and the reverse rate are the same. However, if you look, the number of people at the top and bottom are not the same on either sides or added together. Here on my forward reaction, I have 3 people on the bottom. On my reverse reaction, I have 1. These do not equal each other. On my forward reaction is the products, I only have 2, and over here I only have 3. These are not equal. What this means in a chemistry state is that the concentration or amount of reactants and products does not have to be the same in equilibrium. Okay? The concentration or amount of product to reactant does not have to be equal in order for you to be at equilibrium. Equilibrium just means that the rate of both reactions are the same, not that the amount is the same. And this is a key point that we are going to be talking about tomorrow when we do our activity, to show you that just because the rate of the forward and reverse reactions are the same doesn't mean that you have the same amount of product and reactant. Okay, I hope you guys liked it. Have a good night. Y'all worked really hard on the test today, so I'm proud of you. And I will see you tomorrow for a really fun activity. Bye.